In this video, we will look at the remaining problems in the 6.4 Achieve assignment. Now, most of these problems I'll be using the shells method to evaluate, but on several of them where it's an easier option, I'll go ahead and go back and use the slicing method. For number 16, they give me X in terms of Y. So I think the shell method is the easier way for this problem, since it is a revolution about the x-axis. Normally when it's revolved about the x-axis, I would prefer to do the problem with slicing because I could keep it in terms of x. But since they already give me x in terms of y, I would just keep it in that and then use the shell. So if I know x is equal to y times 3 minus y, this is giving you two y-intercepts right here. You know, you have a y-intercept at 0 right there, and you have another y-intercept when y is 3, x is going to be 0, so you have an intercept at 0 and at 3. My region is going to look something like this. It's a parabola pointing off to the left, but it's bounded by x equals 0, which, remember, that's just the y-axis. So it's that region right there. And we're trying to revolve that region about the x-axis. So I can say, well, all right, if that region is being revolved about the x-axis, I can draw an arbitrary rectangle's revolution, and I know that that rectangle's revolution is going to generate a cylindrical shell. And that cylindrical shell, when I pull it apart, I know it's just going to be a rectangular solid. Now that rectangular solid is going to have a width that's equal to whatever the width of each of these rectangles are. Please notice the width of the rectangles, it's a change in the y-axis. That's why I put delta y there. Now, the base of this rectangle, I could say, well, it's going from the x-axis to the curve, so it's whatever the curve's formula is there. Well, we already know that curve's formula, y times 3 minus y. So that's why I said the base of my rectangular solid is y times 3 minus y. The height, well, the height would be determined by the circumference. If you pull apart that rectangular solid, we know that that rectangular solid, the circumference of it is going to be forming the height of it. We also know that the distance you are away from the x-axis is the definition of y. So at any y value, whether I draw my rectangle here or up here at 3, we already know how many units it's going to be away from the x-axis, and it's whatever the y value is as y moves from 0 to 3 in this problem. So I can say, well, all right, then the radial length is just y, so my circumference that forms the height is 2 pi y. So the volume of one arbitrary shell, it's going to be the 2 pi y times the base, y times 3 minus y, times the thickness there, the depth, delta y. Okay, all I've done in this step is I've multiplied the y times the 3 minus y to get 3y squared minus y cubed. Of course, I'm still multiplying by 2 pi and delta y to form the volume of the shell. That's the formula for one shell. Then we know the entire rotated solid that's generating this volume is going to be 2 pi times the integral from where the shells begin to where the shells end, 0 to 3, of our formula, 3y squared minus y cubed, integrated with respect to y. So I've used the power rule here to get y cubed minus y to the 4th over 4. We're now evaluating that at 3. And you know, when you evaluate this at 3, you're going to get 80, or sorry, that'd be 27, and then this would be minus 81 over 4. I just plugged that into a calculator. I got 27 over 4. We multiply that by 2 pi. And of course, the 2 and the 4 reduce down to just give me 27 pi over 2. And that is the answer that I inputted in, and Achieve liked it. All right, so now, if I go on to the next one here, it's number 17. And in number 17, what they give you is the function y is equal to 25 minus x squared. And then so it's the area bound beneath that function and to the right of x equals 0 and above y equals 0. So my region is this right here. Now, instantly, whenever it said you're going to rotate that region about the x-axis, and I had the function in terms of x, I'm thinking I do not want to do that with slicing. Sorry, I do not want to do that with shells, because shells would force me to do rectangular, would force my rectangles to be horizontal, like in the last problem where the thickness is with respect to y. I would rather not have to solve this x in terms of y and do that. It's so much easier just to do with slicing. So I say, let's do slicing. So if I do the slicing here, then I'm thinking, well, okay, I'm going to break up my region into slices, and each slice is going to be a very, very flat cylindrical solid. And I can say, well, then the area of that is going to be pi r squared times whatever the height is. And I know that the height is going to be a change in x because it's a horizontal height there. So now I can say the volume of any arbitrary slice is going to be pi times the radius squared. Well, the radius goes from the axis of revolution to the curve. We already know the curve is 25 minus x squared. So we get pi times the group, 25 minus x squared quantity squared times the thickness of the slice, delta x. Now we're squaring out that group. Let me see if I can make this a little clearer there. Ooh, there we go. That's a little better. When I squared out that group, I got the trinomial 625 minus 50x squared plus x to the fourth. And then I went ahead and I said, well, all right, I need to find the volume of the entire rotated solid. This is the volume of one slice. I need to find the summation of all slices from where they begin in terms of x to where they end in terms of x. In this problem, they began at 0 and they ended at 5. So I integrated from 0 to 5. And then I can say, well, okay, once I do that, I know that I just plug my individual slice volume formula in there into this integration, use the power rule. I get 625x minus 50x cubed over 3 plus x to the fifth over 5. We're evaluating that from 0 to 5. Of course, the only answer I got is when I plugged in the 5. It simplified down to be 5,000 pi over 3 and achieved like to that answer. For the next one here, for number 18. Number 18 goes back to some problems like what we had in the previous section in section 6.3. Now, and again with these, I would always recommend to do the method that's easiest. If it's about a vertical axis of revolution, you should use shells. If it's about a horizontal axis of revolution, you should use slicing. Now, the only exception to that is when it's about, notice number 16 was about a horizontal axis and I still use shells. That's because the relation was given in terms of y to begin with. So it didn't take any work to get it in that format for me. In this problem, it's about a vertical axis. Automatically, you should choose shells. I have in my problem, the region y is equal to x squared plus b, where b is 1. So I have y is equal to x squared plus 1. I drew a parabola, shifted up 1 unit, and I knew that it ended at when a is 2 or when x is 2. So the y value at that point would be 5. Or we have a parabola starting at 0, 1, going until 2, 5. And the region A is bounded by the line y equals 5 above that. So we can say, well, we're trying to rotate the region bound between x squared plus 1 and y equals 5 about the line x equals 4. I didn't even bother to try to draw what the rotated solid would look like. But I did draw what one cross-section would look like up here. If I took this rectangle, rotated it around, I know that the base of that rectangle is going to be from the circumference of the rotation. Circumference is always 2 pi r. In this case, r. It's always going to be right minus left. Well, that's going to be 4 minus x. This is a problem where any rectangle is located at a distance of x as x goes from 0 to 2. So you can see, well, yeah, then In this problem, if x is some number between 0 and 2, then your radius, it's always at least 2 when x is 2, and it's 4 when x is 0. So 4 minus x works perfectly. Please always just remember, right minus left. So 2 pi times 4 minus x to get to the 2 pi r. The height of my curve, well, it's the top curve minus the bottom curve. The top curve is 5. Your bottom curve is x squared plus 1. 5 minus the group x squared plus 1 becomes 4 minus x squared. So now we have the base, we have the height. We know that the depth of my box or of my rectangular solid is going to be delta x, because each of your rectangle's width is determined by a change in the x-axis, not the y-axis. Now, that's the volume of one arbitrary shell, where I'll be able to say 2 pi times 4 minus x squared times 4 minus x delta x. I carried out the algebra. Please remember, you always must do the algebra before you do the calculus. So I FOIL out those binomials to get to this. Then I can say, well, now once I have that polynomial function for the volume of a shell, I'll just say the entire rotated volume is going to be 2 pi on the integral from where these rectangles would begin to where they end in terms of x, that's from 0 to 2, of my function that I had for my individual shell integrated with respect to x. So now it's the power rule. I get 16x minus 4x cubed over 3 minus 4x squared over 2, which gives me minus 2x squared, and then of course plus x to the 4th over 4. Evaluating that from 0 to 2, when I plugged in the 2, I had 52 over 3. Multiply that by 2 pi, you'll get 104 pi over 3. And Achieve liked that answer. For the next one here, I'll have to go to another page here. Number 19. Number 19, once again, I have the function y equals x squared plus 1, because it's x squared plus b, where b is 1. This time, though, I'm going until a value of x equals a, which is 4 in my problem. So I went ahead and graphed it out. I'm starting at the ordered pair 0, 1, going up until the point 4, 17. And then I can say I'm interested in region A, so I had to go ahead and find the top of that region, and of course that's the line, horizontal line, y equals 17. This is the region that I'm working with. Now, I'm trying to rotate that region. It says about the line y equals -1. Instantly, guys, instantly. As soon as I saw I was rotating about a horizontal axis of revolution, I'm thinking shells is a terrible idea. I would rather use slicing. Slicing is going to enable me to keep it in terms of x. Shells would force me to do this in terms of y. I'd rather not. So I can say, okay, let's think about an arbitrary slice if we rotated this about the line y equals -1. We know that we're going to have an inside radius that we're going to have to hollow out from the outer rotation of this larger radius. And I went ahead and said, well, the larger radius clearly is 18. We know the distance from the x-axis to here is 17. The distance from here to here is 1. So the overall distance is 18. You could have just said top minus bottom. 17 minus -1 is 18. My other one, it's the same thing. You just say x squared plus 1 minus a -1 gives me x squared plus 2. I get my 2 radial lengths. Please remember this is the larger one. So I went back and I said, well, the volume of this slice, it's going to need to have the washer formula where I have the overall volume minus the volume of the portion I need to hollow out. Well, that's going to be pi times the larger radius squared minus the smaller radius squared times the thickness of my slice, which is delta x. So the volume of my slice is 18 squared minus the group x squared plus 2 squared, delta x. And then I can say, well, 18 squared was 324. X squared plus 2 gave me x to the 4th plus 4x squared plus 4. Now I know that this is the volume of one slice. The volume of the entire rotated solid will just integrate from where the slices begin to where they end in terms of x, which is 0 to 4. I go ahead and pull that pi out front. I simplified the 324 minus 4 is 320, and then just minus x to the fourth minus 4x squared. We integrate that with respect to x to get to 320x minus x to the fifth over 5 minus 4x cubed over 3. And then we're evaluating that expression from 0 to 4. The only answer you'll need to worry about is when you plug a 4 into that expression. When I did that, it's just the 320 times 4 minus 4 to the fifth over 5 minus 4x cubed over 3. As I recall, I think when I did this, my calculator had a little trouble with the fraction. Here's how I avoided that. I'll go ahead and show it here hopefully without a sheen on the screen. If I went ahead and said 4 store x and then colon, I typed in my function 320x and then minus the fraction x raised to the fifth over 5 and minus again the fraction, we have 4x raised to the third all over 3. So I have 4 stored in for x, colon is alpha decimal, type in your function, it's going to evaluate it for you. Now I think when I did this, it struggled getting the fraction. I did math, enter. Oh, no, actually it did it fine. But let's say if it had struggled getting the fraction, all I would have had to do is multiply by the least common denominator of 15, and that guarantees that you'd have a whole number, and you could have just said whatever that number is over 15. But in this case, it did it no problem. So 14,848 pi over 15 final answer, and you'll see achieved like that answer for number 20. And please keep in mind, in these answers, achieved is wanting exact values. So please don't put a decimal approximation in there and think it's going to count it right. It's not wanting them in this section. Unless, like for my answer for 20, where the decimal is an exact number. That would be fine. Now, for this one, we're looking at region B. So that's the region beneath the curve. And my curve this time is y equals x squared plus 3. And I have that function from 0 to 11. So I went ahead and just sketched out a rough graph of what that's going to look like. It's going to have the y-intercept of 3, and it's going to go up until x is 11. When x is 11, the y value is 11 squared plus 3, 121 plus 3, 124. So it goes way high here. And I'm wanting the region underneath this curve. And this time that region, again, is rotated about a horizontal axis of revolution, 2 units down from the last problem. This one's around y equals -3. So similar to the last problem, I'll have to go ahead and find the inside and outside radii. The inside radius, it's just going from the axis of revolution to the x-axis. That's the bottom of my region. So I can say, well, that's always a constant distance of 3. That's my inside radius. The larger radius, well, x squared plus 3 minus a -3 gives me x squared plus 6. So I can say the volume of one arbitrary slice. And again, please remember it's a washer. You're going to say, excuse me, pi times the larger radius squared minus the smaller radius squared, all in a group multiplied by pi times the thickness delta x. That's where this comes from. The larger radius squared minus the smaller radius squared, x squared plus 6 would have given me x to the fourth plus 12x to the second plus 36. I went ahead and combined the 36 minus 9 to give me the 27 there for that last term. So that canceled with portion of the 36. I left my pi out in front, integrating this with respect to x since my width is delta x. And so we said whenever we put this into an integral, we have to remember to integrate from where the slices would begin to where the slices end, and that's from 0 until 11. So we get pi times the integral from 0 to 11 of my polynomial representing the individual slice. I integrate that with respect to x to get to x to the fifth over 5 plus 4x cubed plus 27x. We're now evaluating that from 0 to 11. When you plug an 11 into this, you're going to get some big numbers. But fortunately, they simplify pretty nicely here to 37,831.2. And I went ahead and just left it as a decimal since that's an exact decimal. And Achieve was fine with that. For the next one here, number 21. In 21, as soon as they give me the function x in terms of y, I'm thinking, well, okay, I'll leave it in that. I probably can't put it into terms of x. So as I went ahead and tried out the problem, my curve was x is equal to y times 23 minus y. First thing I knew, has a y-intercept at 0, and it has a y-intercept at 23. And it's going to be a negative y squared, which means it's a parabola moving to the left with these two y-intercepts. Now, I knew that was my region. And I also knew that I was trying to rotate that region about the, about the y-axis. So the y-axis is my axis of revolution. So, wow, this is just going to form like a ball or a sphere-like figure when it rotates around. But I can say, well, okay, here's the problem with that. I can't do it with the shell method. I would like to, but I can't. The reason I can't is because if you try to do this with the shell method, the thickness of each of your rectangles within your region, you can't do horizontal rectangles about a vertical axis of revolution. That doesn't make any sense. Your rectangles would have to be vertical, and it would have a thickness of delta x. So you'd say, well, okay, if it has a thickness of delta x, I need to get y in terms of x. You can't. You can get y in terms of x and y, but you can't get y solely as a function in terms of x. Since that's not possible, shells isn't possible. So I'm thinking, okay, I'll use slicing. Now, the unfortunate thing with slicing is that you think, well, anytime you use slicing about a vertical axis of revolution, your slice is going to be delta y. You think that's a bad thing, but in this problem, it's not, because what we were given initially was x in terms of y. So that's going to work out nicely. I'll say, okay, I'll use slicing then. And I can say, well, in my slices, that's going about the y-axis here, the radius of that slice would be the distance from the axis of revolution to the curve. Well, I already know what the curve's formula is right here. So then I can say then the volume of one arbitrary slice would be pi r squared times the thickness delta y. That's what I have right here. Pi times 23y minus y squared quantity squared times delta y. Carried out the algebra, squaring out that binomial to get to this. And then I can say, well, that's the volume of one slice. The volume of the entire region would be where these slices begin to where these slices end. Well, that's from 0 to 23. So I had to say pi times the integral from 0 to 23 of my polynomial in terms of y here. And I used the power rule to integrate. I got my 529y cubed over 3 minus this became 46y to the 4th over 4. The 46 over 4 reduced down to 23 over 2, y to the 4th. And then, of course, plus y to the 5th over 5. You're evaluating this from 0 to 23. Now, this is one of those that your calculator would, I'm sure, or at least mine will struggle trying to get the fraction. So what I did when I evaluated this, I said, okay, I'll say 23, store it in for x, and then let's type in our function. We're going to have the fraction 529. We have y to the third. I'll use it as an x, of course. X raised to the third over 3. And then we have minus the fraction 23x raised to the second all over 2, and then plus the fraction x raised to the 5th all over 5. And I need to go back and fix that second term. It was not the second power, it was the 4th power. Denominator was 2, but the exponent up here is 4. So now I have my function entered in correctly at this point. I can go ahead and evaluate. So this is what I did. And I knew that Achieve would not want a decimal answer. They would count the decimal answer wrong. And I don't think my calculator was capable of converting this one to a fraction. It wasn't. So all I did is I just looked at my denominators and I said, well, get a common denominator. 3 times 2 is 6, times 5 is 30. I took that answer, I multiplied by 30. I knew it would create a whole number, and I just stuck that whole number over 30. So even if your calculator isn't capable of the fractional conversion, you should be capable of it by just getting the common denominator in there and multiplying that term in there. So we can say, well, this number, our answer is the same thing as, I guess that's 6,436,343 pi over 30. And you'll see that's the answer I put on Achieve, and it liked it. For the next question here, we have a region bound by x minus x to the 9th. And of course the x-axis, and it's being rotated about the x-axis. This is a pretty quick and easy problem. I'm not sure why they went easy on us on one of the last problems like this. So I can just say, well, all right, since it's going about a horizontal axis of revolution, slicing is the better option, no doubt. And I can go on in here and say, well, every slice is going to have a radius, the distance from the axis of revolution to the curve, which is just going to be x minus x to the 9th. I don't have any portion that I'm hollowing out because the entire curve is connected to the axis of revolution. So this one's going to be a pretty quick problem. I can say, well, the thickness is in terms of x as well. So that tells me I can keep that in terms of x. The volume of the slice, pi times r squared, delta x. My r squared value, when I square out that binomial, gives me x squared minus 2x to the 10th plus x to the 18th. And again, remember, you must do that before you integrate. Once I come down here, I get the polynomial in there. We're integrating from where x begins to where x ends, from 0 to 1. Power rule in the evaluation. And when you do that, you just plug in the 1, you'll get 1/3 minus 2/11 plus 1/19. Simplifies down to be 128 over 627. And of course, you multiply the pi in there in the numerator. And that is precisely what Achieve wanted on this question. For the next one here, our region is quite a bit more interesting. It's the region bound between the curves y equals x cubed plus 7, and then 9 minus x squared, and x equals 3, but we're rotating about x equals 5. The second it told me I'm rotating about a vertical axis, x equals 5 is a vertical line, I knew I would want to use shells, not slicing. Slicing I would have to do with respect to y about a vertical axis. So I can say, well, okay, if I think about my arbitrary shell in here, I went ahead and drew in my region. I went over here just to verify. I didn't want to trust the drawing on Achieve. So I set my cubic function equal to my quadratic function. It gave me x cubed plus x squared minus 2 is equal to 0. And doesn't factor nicely, but I was able just to, even without going to my calculator, I could see, oh, I can just plug a 1 into this, and I'd get 1 cubed plus 1 squared minus 2 is 0. So I know that this is equal to 0. These two functions are equal at 1. Well, when they're equal at 1, and then you can go back and see, yeah, of course they are, because you get 1 cubed plus 7 is 8. 9 minus 1 squared is 8. So we have the ordered pair 1, 8. And then the quadratic function, as you're going to 3, goes off to 3, 0. So it's going to form our bottom function in our region of interest. And then the other function, the x cubed plus 7, it's going to go up. By the time x gets to 3, it's going to be 3 cubed plus 7. That's going to go off to 34. So I can say, well, that's clearly my top function in this region. Now, I'm bounded by the intersection here at 1/8 and the curve x equals 3. So it's that triangular kind of shaped region. And I'm rotating that about x equals 5. So I put an arbitrary rectangle in this. I know the top of the rectangle is going to be the cubic function. The bottom is going to be the quadratic function. And so then I can say the volume of the shell, you'll see for the height of the shell, I have top minus bottom. Well, where did this 2 pi times 5 minus x comes from? That comes from the base of the shell. After its rotation, it's the circumference. And so you'd say, well, the circumference, of course, is 2 pi r. R is going to be the distance from the axis of revolution to this shell. What's the location of the shell? It's at x, as x goes from 1 to 3. Well, the axis of revolution is over here at 5. So our radial length is going to be 5 minus x. It is always, always right minus left. So I can say, okay, 2 pi times 5 minus x. This is just the height. This is the width. Of course, that has a width. That's a change in x. I simplified out that height function to get to this. Forgot my delta x there, so I had to scrunch it in. And I'll get the 2 pi. I multiplied the 5 minus x throughout that group to get to this. Simplified, brought it into my integration formula. I'm going to integrate 2 pi. Why am I integrating from 1 to 3? Well, because that's where your region begins and ends in terms of x. And of course, we need it in terms of x from 1 to 3. My polynomial representing the volume of the shell goes in there. I use the power rule on each term, pretty straightforward. And then I evaluate that expression from 1 to 3. When I evaluated this expression at 3, I got the 282 over 5 answer. When I evaluated this expression at 1, I got the negative 98 over 15. But of course, we subtract the lower limit of integration. Whenever I simplified that out, multiplied by 2 pi, we get our 1,888 pi over 15, which was correct on Achieve. Last question in the section looks extremely similar to the previous one. Now, the thing that's different in the previous one, even though my region looked the same, I was rotating about a vertical axis of revolution. So I wanted to use shells. Well, why am I using slicing here? Because it's about a horizontal axis of revolution, and that's by far the easier choice. So it's an extremely similar shaped region. This time, the curves I found were bounded by the ordered pair 1, 3. That's the first intersection point when I would set those equal to each other. And then I know that the cubic function as x goes up to 2, because my right-hand boundary in this one, it says it's bounded by x equals 2. When I plugged a 2 into the cubic equation, I had 2 cubed plus 2. That gave me 10. Of course, you plug the 2 into the quadratic. 4 minus 2 squared becomes a y value of 0. So I have this region right here, and I'm rotating that region about the line y equals -7. So instantly, as soon as I saw it as a horizontal axis of rotation, I went ahead and thought I need to do slicing. I'm going to need to find the shorter radius and the longer radius. The shorter radius is going to go from the axis of revolution to the lower curve. The lower curve is my 4 minus x squared here. So I can say, well, all right, then that's going to be top minus bottom. Even though this is the lower curve, it's still above the axis of revolution. So I'd say, well, that's going to be 4 minus x squared minus a -7. Well, that's why I put plus 7 there. And so 4 minus x squared plus 7 gives me a distance of 11 minus x squared for the shorter radial length. The larger radius, the larger radial length here, you'd say, well, it's the top curve minus a -7. The top curve is my cubic function, x cubed plus 2. X cubed plus 2 minus a -7 means plus 7. I get x cubed plus 9 for my larger radius length. Now I go back in here and I can say, okay, then the volume of this slice is the volume of the washer. And that's always, always going to be the entire volume of the rotated solid minus the interior portion that we have to hollow out. So you'd say, well, okay, the larger portion is going to be pi times x cubed plus 9 quantity squared minus the smaller cylinders that we need to hollow out. That's going to be 11 minus x squared quantity squared. We're multiplying all this by delta x because that's the thickness of each of our slices. Then you go in and you can say, well, all right, my first one is going to simplify to be x to the 6th plus 18x cubed plus 81. My second one, when I square that out, I'll get 121 minus 22x squared plus x to the 4th. You subtract any like terms, which there's not many in there. I just went ahead and subtracted those out. I wanted to put it in descending order to make it a little bit more straightforward here. And I said, okay, this is going to be the volume of one slice. Now, the volume of the entire rotated solid would be the integral of where these slices would begin to where they end in terms of x. Well, that's just from 1 to 2. Integrated pi on the integral 1 to 2 of my polynomial with respect to x. We use the power rule for every single one of those terms. Really easy to integrate this problem. And then after you integrate, for the upper limit, you just plug in a 2. I promise you, when you plug a 2 into that expression, you should get 6,568 over 105. And then I said, well, okay, now I'll evaluate the lower limit. I plugged in a 1 into that expression, and it actually was a negative. So obviously, you subtract a negative is the same thing as adding a positive. I had plus 5,927 over 210. Added those fractions to get this gorgeous looking answer of 19,063 over 210. And we had to multiply that by pi in the numerator. And you'll see that when I entered this answer into Achieve liked it. Hopefully this makes sense for this section. These problems can be an acquired taste. Sometimes students really struggle with them in the beginning, but once you get the hang of it, I think you'll really enjoy working these problems, particularly if you follow my advice as far as sticking anytime you do a horizontal axis rotation, slicing is the better choice. If you do a vertical axis rotation, then shells are going to be the better choice and the easier method. That's probably true about 95% of the time. The only time that's not true is like in number 16, where you're given the relation in terms of y at the very beginning, and even though it was revolving about a horizontal axis, it was still easier to keep it in terms of y. Okay, hopefully that summarizes that section really well for you. If you have any questions, let me know. There's some fun stuff through here.